Hello, this is Jack Hicks, and this is my submission for Lab 3, Circuits. So, for an introduction, the objective of this lab is to predict the behavior of circuits containing resistors in series and parallel, to use multimeters to measure actual values of conventional current and potential differences in the circuits, and the final result is to examine the behavior of ohmic resistors and capacitors. So the main ideas are electric field, which I've discussed at length in previous labs, which the formula is on the left, voltage, which is the negative of the change in the electric field over a length, resistance, which is the voltage divided by the current, which is a resistance to a flow, capacitance, which is the charge divided by the change in voltage over the capacitor, and it can be thought of as an ability to hold charge. Current is flow through a wire, and potential energy is basically the potential to become energy, and it is the voltage multiplied by the charge. So as a little preview of the results of the lab, first the system was basically everything in the surroundings, nothing shown on the right. And as for the numbers, the main ideas are that the circuit worked properly, the node rule worked in that both currents were found to be 18.2 microamps. There was a total circuit voltage difference of 0. And there are plenty of resistances that we found that don't seem to match up as to what they should be, which will be explained later. They're not math errors. And then for the RC circuit, it was found that the larger, assumedly the 20 ohm bulb charged faster than the 10 ohm bulb and discharged a lot slower, which makes sense because it can hold more charge, but the charging part makes a little less sense. But that'll be discussed later as well. So what models will we be using? So the main models will be the loop rule, which is that the sum of potential differences across the circuit would be equal to 0. The node rule, which is the current going into a node, is equal to the current going out of a node. And we need to know what a circuit is, which is a line of current. Resistors, which are parts where current flow decreases or is resisted, and capacitors are things that can charge and discharge charge. The initial values are on the right, and the assumptions we made are that no energy lost to the surroundings. The voltmeter does not alter the circuit when it's not connected, but we're just measuring. The origin is the start of the first battery. Each wire is the same, and same with the ammeters, and they're all working. And these assumptions are made for ease of calculation. Getting into the actual experiment. So these have been shown before and are shown later, and this is just the circuit, the first circuit on the left and the RC circuit on the right. So getting into the actual experiment, the procedure is on the right and the results are on the left. So I'll go through the results. For part 1, the circuit, there's a picture right there. Part 2, the ammeter readings were 18.2 microamps each, and when we reversed them, the sign reversed it. And then connecting the voltmeter, we got a voltmeter reading of 2.8 volts and an ammeter reading of 0 amps, which makes sense because the battery has a voltage difference of negative 2.8 volts, so if the sum has to be 0, then the reading should be 2.8 volts. And that's also why the ammeter reads 0 amps, because the circuit stops at the voltmeter, so there's no current. And the volt current diagram is also on the right. So furthermore, for 5, the sum of the potential differences is 0 volts. Theoretically, it should be 0, so they match. 6, the graph shows just that, and the specific numbers are plotted, and you can see them above the graph. For number 8, the voltmeter circuit alters the circuit by a very small amount, so it doesn't change much. 9, the ammeter reading is 1.87 volts, 18.7 milliamps. 10, the explanation is that they both equal 48.3 amps, which makes sense because of the node rule. And the resistance values for 11 in ohms are 36, 38 for the two resistors. And for the wires, 888, 1,000, 1,666, 1,000, and for the ammeters, 1,027. Now, a lot of those don't make sense, which will be discussed in the discussion, but it is, again, not a math error. It'll be discussed what happened. So for part 2, the brightness over time as the capacitor charges decreases, and then as it discharges, it increases and then decreases. Same with the other bulb, but it's brighter, and the observed times for the smaller bulb are 15.62 seconds and 10.32 seconds for charging and discharging, and for the larger bulb, 23.7 seconds and 56.75 seconds for charging and discharging. Calculating their resistances. Resistance is the change in voltage over the current. So the code takes our values from the chart and literally just calculates it for every part that we need. And here's the data already discussed. As you can see, no math errors. Let's look at the data. So the voltage and current across the circuit both make sense with the loop and node rule. The resistance for the 47 and 100 ohm resistors are a little bit off, but for the 100 ohm it's a lot off, and this could be due to one of the errors discussed below. the resistance across the wires are huge instead of being 0, but that actually makes sense when you look at it, because we should have just put 0, but putting the actual numbers, you divide a really small number by an even smaller number, making it really big, when really you should just put 0. And the charge and discharge times for the RC circuit makes sense, except the charge time for the larger bulb is a little off, but it could be due to one of the errors discussed below. As for the what if question, if we charge the capacitor with no resistor, theoretically it would charge instantly, but because wires have some resistance, this probably wouldn't actually happen in real life, and we did this and recorded a time of 4.8 seconds, which is not 0, which means our theory is right.